Hey everyone, time for our next lesson. Today we're going to be talking about factoring quadratic expressions. Our mindset message of the day is everyone was made to do math. Don't forget that. Our learning goals, basically one learning goal for today. Essentially you need to come out of this being able to factor quadratic expressions when possible. The vast majority of quadratic expressions, if you were to just pull one out of your head, for example, is likely not factorable. So we're focusing on ones that are factorable. Your prior knowledge would be just computing sums and products, because we've seen some puzzles and questions we've answered before that deal with that. Remembering the distributive property, and just basic exponent rules, I guess, because we're going to be multiplying variables together and remembering how the exponents work there. So let's dive right in here to a product problem, because this will help us understand this. Consider the product 37 times 23. And the first question asks us to use an area model to compute this. So, I like to think of the product 37 times 23 as the area of a 37 by 23 rectangle. Every time I see a product of two numbers, in my mind I think, oh, a rectangle's area, because it's so simple. It's length times width. And we can learn a lot from thinking about it in that visual way. So what I've done is I've thought of it as 37 times 23 to be the area of the whole rectangle. But I broke the 30 into 30 plus 7, and the 23 into 20 plus 3. And that means that I can basically make the calculation easier on myself. Of course, you could just throw it in a calculator, but this is helpful for us to understand some stuff. 20 times 30, oh, that's easy. That's 600, right? Easier than just trying to do this in our head. And 20 times 7 is 140. 3 times 30 is 90, and then this little smallest rectangle is a 3 by 7, which is going to have an area of 21. So it turns out our product, 37 times 23, is 600 plus 140 plus 90 plus 21, which is 851 if you add all those smaller pieces together. So if we were to just straight up calculate that, we'd get 851. So there are actually other ways. I've set up another rectangle, but instead of using like 20 and 3, I thought of negatives. Now that doesn't seem to make sense because for an actual rectangle, you can't have a negative side length, right? But it turns out it actually works out this way. You can almost think of negative area as just like area that's like taken away, right? So if we think about this, I've thought of 25 minus 2 times 40 minus 3 to give me my 37 and 23. And 25 times 40 is 1,000. This becomes negative 2 times 40 is 80. And then 25 times negative 3 is negative 75. And then this is actually kind of interesting because you and I both know we need 851, right? Right now what we have is 1,000 minus 75 minus 80. And if we subtract that, then what we get is 1,000 minus 155 is 845. But we need 851. Right now, this is 845. So what we need left to bring it to 851 is we need it to actually go up by 6. Okay, so you can see right now what we have is 845. And this actually lends a little bit of explanation to why negatives have to multiply to make a positive in some way. Because if what I have left there was negative, I would be taking away from 845 and it couldn't be equal to 851. So this is a cool little thing to help us get a little bit more of an idea for why it should be true that negative 2 times negative 3 actually is positive 6. So that's kind of a cool little thing that we can see if we see this thing. So actually this process generalizes, and you'll see what I mean when I say that. So let's actually consider multiplying these two algebraic expressions, okay? These are two linear expressions, and we're going to multiply them, and you'll see that it becomes a quadratic expression. But the reason why I say that what we're doing generalizes is because, like, well, consider this. If you put in 10 here, this becomes 30 plus 7, 37. If you put 10 in here for x, this actually becomes 37 plus times 23. So no matter what x is, we can still kind of think of this all in the same way. So this brings us to something that's an important tool to use when you're multiplying algebraic expressions. and this is what I call an expansion box. Okay? Essentially what it does is, it's a nice tool to help us perform the distribution that has to happen when we're multiplying two expressions together. So I've set it up already. Now you'll notice I usually just make it a square because the value of x is variable, so there's no way to make it seem like more accurate or not or whatever. So I just left it like this. And if I want to actually multiply and find this product, it's the same as asking, oh, what's the area of this box, right? And so we just multiply the individual pieces together. 2x times 3x is 6x squared. 2x times 7 is 14x. 3 times 3x is 9x. And then 3 times 7 is 21. So the product here is actually equal to 6x squared plus 14x plus 9x plus 21. And these two middle terms are always like terms, right? The ones from these two boxes here, these two boxes are always going to be like terms. So 6x squared plus 23x plus 21, that represents our actual final product that's equal to that. Okay? So keeping that in mind, that'll help us by jumping into our first theorem of this unit. So an important theorem that you've likely learned before actually is what I call the sum and product theorem. And this is for more the basic quadratics. And when I say basic, I mean that this leading coefficient equals 1. So let's show how it works first, and we'll jump into what the theorem statement actually says. So if we actually just took two basic expressions, linear expressions, so just x plus something or minus, this p and q themselves could be negative, right? So that would turn into x minus whatever. Watch what happens when we use an expansion box or whatever method to actually multiply each piece out with each piece. And I want to remind you that the reason why this works the way that it does with the expansion box is just like with that area model, it's just distribution. So every piece here needs to end up distributing with each piece here. And that creates 4 total pieces. So x times x is x squared, and then distributing this into the p gives me p times x, and then q times x, and then I'll just leave it in order, p times q. So the actual product of x plus p times x plus q is adding all these pieces together to form one whole, right? X squared plus px plus qx plus pq. However, don't forget that this and this are like terms. And this, you can think of this as an x that can like factor out. So it leaves me with p plus q all times x plus pq. And now what we can see is that if that value we call b, that's the standard thing to call it, that must be equal to the sum of this and this, right? We can match that up with that. Because this added together is just one single value, right? And then whatever the single value is at the end is always going to be formed from the product of p and q. So that's what we would call c. All right? So that's what we're going to utilize to actually start factoring. So for this, we want to factor each of the following, and you'll notice these are all the basic quadratic expressions where the leading coefficient is just 1, okay? So we'll talk through 1 or 2 of these, and then I'll let you go to do the rest, and we'll check our answers. Now, we're going to use this fact here, actually, okay? So in our case here for A, our B value is 10. So if I want to factor this, I'm trying to break it into the product of 2 linear expressions, and we need it to be true. We already know that this is going to be x, because x times x gives me x squared, right? We need it to be true that whatever this number and this number are, that they match this property. So these two, p and q, right? They need to add to make this, but they also at the same time must multiply to make this. So what are 2 numbers which add to make 10 and multiply to make 16? If it helps you, you can just start listing things that add to 10 and figure out the pair that multiplies to 16. But I think I found 8 and 2 that work. So this is a nice way to apply this. And this turns out to be a very handy property, actually, as we'll see in the future. So what I'll have you do right now is, I want you to go ahead and tackle the rest on your own, and then we'll reveal the answers in a moment. So pause the video now and do these. So here are the solutions, all the factored versions of each of these quadratic expressions given to you. A couple things to note. It's okay if you have the factors switch around. Like if you wrote x plus 4 times x plus 6, we already know that multiplication is what we call commutative. You can switch it around, right? Or if this one you actually wrote it all out, x plus 5 times x plus 5, that's fine. But since it's the same thing, I wrote it as x plus 5 squared. So let's look at a few more things and expand on this and dive a little deeper into factoring before we're finished today. So we're going to address the elephant in the room. I know you were all thinking this. But what if a doesn't equal 1? Who cares if we're just doing these easy cases? No, I'm just kidding. Who knows if you're thinking that or not. However, that's an important thing to consider. What about the ones that are factorable where it's not just the easy case, where we can just ask, oh, what multiplies to this and adds to this? Well, don't worry. We can actually manipulate things and make it into that kind of thing. So let's go ahead and look first of all. I'm going to just let you know, this one's going to be like the easy case. But for parts B, C, and D, there's a very specific thing I'm going to show you that we're going to utilize the structure of this to solve it. But this one, okay, let me just share with you. It's always good to look out for if there's a number that can be pulled out of everything. You notice these are all divisible by 2. So this, I can pull a 2 out and leave x squared plus 10x plus 16. Oh, well, you and I both, we've done that one before. So we know that that factors into x plus 8 times x plus 2, and then we just have that 2 out front. So this would be fully factored for that. But these other ones, they don't really quite work that way. Like for this one, you may be able to pull a 2 out, but you can't pull the 4 completely out. So if you can pull this leading coefficient all the way out, then go about your business. However, let me show you a really cool thing to think about. Notice that 9x squared is actually 3x all squared, right? Because 3 squared is 9, and then x squared is just x squared. So watch this. I'm going to rewrite this quadratic, so instead of its variable being just x, we're going to kind of consider it being 3x. So I intentionally left a 3x in there and a 3x in there, and this 16 I'm just going to leave alone. Now if you want, you can kind of think of this 3x as being like another variable, like y, let's say. Because if we let y equal 3x, then this that I have written here really becomes y squared plus 10y plus 16. Wait a minute, that's again the same structure as that, right? But in this case our y is actually a whole other expression, 3x. But you already know that this is the same as y plus 8 times y plus 2. But 3x is behaving like our y. So watch this. Y plus 8 times y plus 2. Bada bing, bada boom. There's our factored form. So that's a really cool way we can look out. Now you'll notice something here. This relied on this number being a nice perfect square so that I could do this. And then of course this being divisible by that number. But we'll learn how to deal with that again in the next example. Go ahead and pause right now and finish those two off yourself. All right, let's go ahead and check these. So in this case, our y is 2x. In this case, our y is 5x, right? But we can then, we've turned it into something where we can ask, oh, what multiplies to 24 and adds to 11? What multiplies to negative 21 and adds to 4? So go ahead and check your factorizations of that. And then let's move on to our very last topic. Now I know what you're thinking even further. Okay, but in the last example, you just made that a value be a perfect square. What if it's not a perfect square? Okay, well, again, maybe you weren't thinking that, but you probably should have if you've been thinking as a mathematician, right? These numbers are no longer just nice perfect squares. I can't just make it into something parentheses squared right away. But when there's something you want, just make it happen. I'm going to choose to do something here. I'm going to multiply an extra copy of 2 into this whole expression. Why 2? Because that's the leading coefficient. For this one, I'll multiply 12 into everything. And for this one, I'll multiply 6 into everything. Because watch what happens. This turns this into 4x squared plus 26x plus 30. And I can then just do what I did in the last example. So this becomes 2x squared, all squared, plus 13 times 2x plus 30. Now be careful here because you might be thinking, yeah, how can you just multiply a 2 in there? You're right, I can't just do that and then leave it and say it's the same thing, because it's not the same thing, right? You can't just multiply something by anything and call it the same thing. So the 2's there basically along for the ride. You're going to actually pull it out and remove it in the end, okay? So now we've turned this into one of the easy ones, right? So my variable here is 2x. Again, you can think of it like a third variable, like y. But we can ask what multiplies the 30 and adds to 13. Oh, so this becomes 2x plus 10, and then 2x plus 3, because 10 times 3 is 30, and 10 plus 3 is 13. The only thing is, I'm not quite done yet, because like I said, this 2 just went along for the ride to help me out. Now you're going to have to pull a 2 back out of here. Luckily, you can see in this factor, it could have been in this one, but in this one, there is a 2 that's extra, right? So my final factorization of this, I should have left myself a little bit more space, is going to actually be, if I remove this 2, it's just going to make it x plus 5. So x plus 5 times 2x plus 3. That's my actual final answer for this. Okay, so these green, the brown steps are my steps, but the actual final factorization is this once I've dropped that 2 out again. So I had to add him in for the ride and then drop him back out. Okay? Now we finally, if there's going to be a factorable quadratic, we now have the tools to actually factor it. So pause and do B and C, and then we'll look at the work and answers together. All right, let's check our work. Now you may have gotten to the very end of these and been a little unsure how to factor that final number out. Like for example here, the 2 was along for the ride, and then we pulled the 2 away and just dropped him off, right, to get this. For these ones, you actually had to do something a little bit more tricky with them. But anyway, check your first steps here, and you should have ended up with 6x minus 8 times 6x minus 3. But there is a common term here. You could pull a 2 out of both of these and leave 3x minus 4. And this, you could pull a 3 out of both of those and leave 2x minus 1. And notice that 2 times 3 makes a whole entire 6, and that's going to be dropped off. So in the end, I'm going to say 3x minus 4 times 2x minus 1 times 6. And I'm going to just drop that 6 off. Remember, he was just along for the ride, and my final factorization is that. By the way, other side note to mention, you can certainly do trial and error on these and just like work it out in your head just by playing around with it. That's totally okay to do. But this method and structure actually helps us get insight into how quadratics work anyway. So it is important to think about. Checking this, same deal goes, and when you get it down to this, there's a 4 that can be pulled out of there, and a 3 that can be pulled out of there. You'll notice 4 times 3 makes 12. And remember, I had multiplied a 12 in there along for the ride, so I need to just drop that 12 right off. And so my final factorization is 3x plus 2 times 4x minus 1. So happy math, that's it for this lesson today, and we'll see you next lesson.